Still.
Yeah, like it's like you know.
That's really good. Never. Okay. What do you guys think? Not pottery, you want to say?
Make him do that. Because I've realized he's not good enough for things. Even it's because people say
Yeah.
make it really fun.
Really?
Yeah. You know, and and I beat him 5 times in a row. And then I tried to let him win too. Still, and then it was hard. Yeah. So then more party beat him too, so that's all. And then the second day, he said we should go swim laps because it's a basketball. I was like, okay, we don't he doesn't swim, but he's athletic, like he works at a gym, you know. But he's studying nursing. Oh, it's cool. So he works at a gym. So you know he's athletic guy. He's like both a big one, right? So he's like, I'm gonna do 10 boys. Oh. He swam a 500. I left him 3 times in the 500.
You ever seen like those days where the football team will jump in?
Yeah, and then they can't swim.
Yeah, it's like so pathetic.
Yes, I know you're talking about the black and them kids. Yeah, so I beat him in swimming too. So like, I'm starting to think he's not good at swimming, so I don't want to be like, because I asked him if he's ever been to a party student. He said no.
You asked lunch?
Like he plays games. He likes to read. He's learning the guitar. We saw him with it. They're like,
That's cute.
gee. And like, and then he's like, oh, like he's running his skateboard. I'm like, oh, you know, skate. He's like, oh,
Okay. This is really good for the guitar. It's really good. It's really deep. The whole time.
I can't play it. So we don't have a experience. Like my first guitar. We started to learn the piano. Second year. In high school. In the marching band. The white hat was he wants to play piano classics. Dude, he's really good at it. I've never seen him get it.
It's a lot of work.
Classically trained in the piano too. Damn. So you play the piano back then. So I have one, but I'm not as good as him. Yeah, and I asked him if he's been to a pottery student, and he said no. What's that? And I'm like, just go paint.
I saw
make it, I think.
those like the decorated lamps. I've seen them doing that, but I'm like, I'm not sure if I love it or hate it yet. They look really pretty. Have you seen those?
Yeah, I know we don't. Should look at
For a candle.
no, you should look at the studio here too. It's called Nuthead Pottery Studio. It's in Riverside. You should go with your boyfriend because they have like date night things where you can go on the wheel and you can make stuff.
What 2 teeth?
Mud hut, like mud. It's family owned. And you could do classes on the wheel. You could also do like sport.
I am
classes. Yeah. Or you can just go and paint stuff. And I like go in and paint stuff because it's not like freaking Color Me Mine where they cut you off and stuff like that. You know what I mean? You know what I mean? Plus their turnaround times are really fast.
I don't make them.
Yeah, there's a session where it's like an hour and a half and it's $50 per person and you can make up to 2 items. And then there's another one where it's like two hours and a half, and you can make them and paint them. So you do the underglaze. Have you ever taken a ceramics class?
I did ceramics. I
In
did
high
some nice.
I did 2 years of it in high school. So like I'm good at the wheel and I'm good at sculpting. That's why I was like, I'm like, okay. So like this is so hard. I'm just gonna be like,
For me,
I'm just gonna be like bringing it up, you know?
I haven't touched them yet.
I haven't touched one in like years. Still got it. Yeah, it's affordable and it's nice.
Are these? Like, are you? Or so like,
So like if it's
They're
like
all
individual
together?
classes, yeah. So like you see how there's like individual classes?
are they gonna tell me what to make or I can make what I want?
They tell you what to make it guided by an instructor.
Just what I need.
Then that they have memberships for that, where you could, it's in their next door studio where they have memberships where you could pay a monthly fee and you bring in your own clay, but they give you a certain amount of shelf space in glazing. So it's expensive though.
So I have to do like 1 month. What you're saying?
It's either you do the class and they show you how to throw something on the wheel.
Yeah.
But they also have like a 4-week course and you can make them do like kitchen set.
A 4-week course.
Or you can
Actually,
make a whole
I
kitchen
kind of
set.
like that. Is that?
Classes. I want to take the 4. It's going to 4-week classes.
My husband, sure. Tuesdays.
And it's a very small class. I think it's like 8 students and then 1 instructor.
Yes.
They have a lot of like good date night classes where like you can make like stuff.
Okay.
We change them up every week too.
And
And that's for the cooking.
this?
Yeah, the
You make
matcha.
this?
The matcha set. So you make the matcha bowl and whisk holder.
Oh, is this? I see. I see.
Mhm. And they give you like the whisk.
Oh, you know what? They've kind of got me here.
Yeah.
Okay, they've
For
kind
a
of.
couple. See, $100. It's not bad, huh? And you
No,
get the
it's not bad.
payment.
They've kind of got me on that one. I do love tiki co.
All right, it's 4:30. It's going to get started. All right, so thank you everyone for doing the midterm. So just like first midterm, I plan on grading this tomorrow and Monday. So you should know your grade before Tuesday, and I'll bring them to pop on Tuesday for you to have. Just so that you know before the final exam, you should know kind of exactly where you stand in class. Okay. Now is also a good time to remind you that, between the 2 midterms, whichever midterm you score higher in, I am going to count that one as a higher percentage of your grade. So that will be relevant on Monday or Tuesday whenever I finish grading. So I'll do that automatically. So whichever midterm you score higher in, there's really no elegant way to do it in Canvas. So the way I do it is that your first midterm score right now is counting for 30%. If you score better on your second midterm, I'm just going to swap that into your first midterm score and then swap your midterm 1 to midterm 2. So on Canvas, it's going to say, midterm 1, midterm 2, but just know that whichever was midterm 1, that's the one you scored higher. Okay. Okay, so I'll have those back to you guys by Tuesday. And then, just because of how quick the summer session is, we'll be back at it a week from now with the final exam. So let me just, now that the second midterm is done, let me write down the format for the final exam. Probably not what you want to think about, but since everyone's here and since that's kind of the last big thing, I do want to mention that. Okay. So final exam is going to take place 1 week from today. So that's going to be Thursday, June 25th. So it's going to take place during the lecture session. So it's going to take place starting at 3 o'clock, and then you'll have the entire class session to do. So we're not going to do a weird kind of split session where we, have only halfway done. But of course, if you finish the final exam early, you're free to turn it in as well. Okay. Okay. So in terms of number of questions, so final exam will be a bit longer. So final exam will have 6 short answer questions. Right, so those will be your conceptual questions. Your midterm exams had 4, so the final exam is 2 additional short answer questions, and there will be 4 problem solving type questions. So both our midterm exams had 3 problem solving questions, so final will have just 1 additional one. Okay, and just like the midterm exams, there will be a study guide. So I actually did prepare that actually today, just because, I not too many people came to office hours today. So that will be posted basically right after the class today for you guys to see. We're also going to have a final exam review session. So, we're basically right on schedule with everything. So we'll have time for final review session. So that'll take place next Wednesday. Right, so next Wednesday would be June 24th. So I am planning to lecture that day. So we are going to cover, we're just going to talk about briefly about Navier-Stokes that day. We'll do that for the first half, but the second half will be just a review session from the time. So if you want to optimize your time, the review session is scheduled to start at 4:30 p.m. next Wednesday. Right, and then you can join just from the regular lecture Zoom link as well if you want to join virtually. Okay. In terms of materials, or in terms of content, so you'll see when I post the final exam study guide. I did cut out all the content from midterm 2, so there will be no control volume questions on the final exam. It feels kind of weird to test you on it and then test you on it again a week later. So midterm 2, that's the last you're going to see control volumes. There is a little bit from midterm 1, so just kind of if you remember the very first lecture we had where we just introduced fluids, that will be on the final exam. And then just a little bit from fluid statics. And so specifically the hydrostatic forces on surfaces, that will be on the final. Besides that, everything on the final will just be starting with potential flow. So potential flow, dimensional analysis, pipe flow, and then a little bit of what we're going to do next week, which is external flow and Navier-Stokes. Okay, so most of the emphasis will be on the stuff after midterm 2, or I guess technically we started that, last week. But there will be a little bit of fluid statics and a little bit just general fluids knowledge for that. Okay. But all of that is outlined on the final exam study. So the final exam study forgot that. But just verbally, I just want to tell you the content for that. So that means in terms of homeworks, final exam will cover a little bit of homework 1, maybe about half of homework 1, and then homework 4, of course, which is due this Sunday. Okay. All right, in terms of what you can bring, right? So just like the midterm exams, please bring your writing utensil. Please bring your calculator. And because the final exam is a little bit longer, it is covering a bit more content, you can bring 2 sheets of notes. Okay, and then you can use front and back side. And if you want to bring 4 pieces of paper where you only print on one side of the cheat sheet, that's fine for me as well. Okay. Okay, yeah, so that'll be next week. I know very quick turnaround, but yeah, I think that's everything you need to know for the final exam. So so this format for the final exam, this is what I normally give for a 2-hour final during the regular semester. It's just the only difference is that for this one, you'll have the full 3 hours to do it. So time shouldn't be an issue. Especially with some of the problems that will be on the final. So the dimensional analysis problem, those ones typically are fairly short, and so I don't anticipate the final taking you all 3 hours. But it'll be available for you if you need it. Okay. All right. Any questions on the final exam? Okay. All right. So with that, let's go ahead and start the lecture for today. And so for today's lecture, we are basically just finishing up what we started yesterday with regards to pipe flow. Okay. All right. So like we mentioned before, or like we talked about yesterday, pipe flow is a very important application of fluid mechanics. Just because you see this in almost any engineering application that involves fluids. Okay. So specifically, we're looking at engineering systems where we're transporting a fluid from one place to another via a pipe. And so as engineers, what we're interested in is the design and analysis of these kinds of systems, right? And so one of the main, aspects of pipe flow that, that needs to be analyzed and always needs to be found out is this idea of a pressure drop. And so because of the presence of viscosity and, because of the presence of turbulence and other minor losses and major losses, you're almost always going to have a pressure drop as the fluid goes from one location to another along the pipe. But that pressure drop, essentially is an expression of how much energy is lost as the flow goes from one part to another. Okay, so just in the same way where if you need to transport a solid object across a surface, there's friction that needs to be overcome, right? When in pipe flow, there's viscosity that needs to be overcome, and where we get the energy to overcome that friction is through the pressure. Okay. And the main way that we obtain the pressure drop is through the use of our modified Bernoulli's equation. And so what we said is that, if we compare two different locations in our pipe, we can connect them and their quantities via Bernoulli. Okay. All right. And so we have P1 divided by rho times G plus V1 squared divided by 2G plus Z1 is equal to P2 divided by rho times G plus V2 squared divided by 2G plus Z2. Right, so that's our standard Bernoulli, or I should say standard Bernoulli in kind of this head loss type form, where we divide every term by the density multiplied by gravity. Okay. Right, and the way we turn it into the modified Bernoulli is by adding these two additional terms at the end. We have HS, which, for the most part, we're not going to worry about HS too much because HS stands for what's called a shaft head. Right, so any kind of mechanical work that you are explicitly doing on the fluid, either through a pump or maybe mechanical work that you're extracting from the fluid via something like a turbine, that gets added into the shaft head. Okay, so that was more the focus of conservation of energy and control volumes. But what we're mostly interested in pipe flow is this term. Okay, where HL here, these are our head losses. Or those head losses, those encapsulate all of the viscous dissipation, all the loss of energy that we obtain or that happen due to viscosity in our flow. All right, and so what you're going to see, and so for today's lecture, I do have two examples. The two examples are kind of very typical, pipe flow type problems. A big part of the problem is going to be computing these head losses based on the geometry and based on the different features of the pipe. Okay, so this is kind of one of the really key aspects of pipe. Okay. Now, I almost said that computing the head losses is the main thing, but actually there's a lot of other aspects of pipe flow problems that we can that can happen, and you'll see that in the examples today. But it'll at least be a big part of your solution pathway because without the head losses, then we have inviscid flow, which is impossible in these types of situations. Okay. Okay, now for the head losses, there were a couple different sources. Right? And so these two different types of head losses are, the main ways that we categorize these. So the first being what we call the major losses. So the major losses are kind of what we ended up talking about last time. So that was the last example that we did before we left for class yesterday. So the major losses are the viscous losses that occur in straight sections of pipe. Right, and so there's a whole methodology, there's a whole way to compute those major losses. A lot of times those involve the use of the Moody chart, especially if you have turbulent flow. Okay. Right, so we already know how to do that. The other part, which we're going to start talking today about, are the minor losses. Okay. Which again, the naming convention for these losses is pretty terrible. Major and minor has nothing to do with the magnitude of energy dissipation. In fact, for a lot of systems, your minor losses are going to have much more dissipation than your major losses. Okay, but the minor losses, those basically compute the viscous losses due to any kind of change in geometry, change in direction of the pipe flow. Okay, so that'll be the first thing that we talk about today, and then we'll get into some examples into how we can actually use that in problems. Okay, but that was just kind of a very quick recap from yesterday. A lot of what we also talked about yesterday was the difference between laminar and turbulent flows. And so, for the most part, from now on, for the next two examples, you can basically assume that we're going to be working with turbulent flow. Okay. All right. Any questions on this before we jump into the minor losses? Okay. All right. So let's go ahead and jump in. Okay. So just like I mentioned right above here, your minor losses are the viscous dissipations that occur, through any kinds of change of geometry or change in direction. Okay. Now, the downside here with the minor losses is that, because they are fairly nonlinear, it is kind of hard to kind of compute these and even run experiments on these. We actually take a very kind of interesting approach to the minor losses. Okay. So the approach with the minor losses is that, you kind of take like an additive approach. And so every time you experience a certain kind of change in direction or maybe a change in geometry, you're going to add just a flat term for those minor losses. We'll get into a bit more about the fluid mechanics reasons, although it's a little bit hard to kind of discuss them in detail, without getting into kind of too advanced kind of Navier-Stokes stuff, right? But let's focus just on the methodology. Okay. All right. So for each type of change, right? So for each type of either geometry change or direction change, there is basically a table in the book that kind of tells you how you should add the minor losses. So we'll go through a few of them here in the lecture, but just know that there's tables and data tables for this. Okay. So based on any type of change, and so for instance, like a 90-degree turn is a type of minor loss. An expansion is another type of minor loss where the cross-sectional area suddenly gets bigger. A narrowing is another type of minor loss. A 45-degree turn is another type. So, there's tables that say, for these types of either change in direction or change in geometry, this is kind of what we've tabulated. Okay. And for each of these, what the table will tell you is something called a loss coefficient. Okay. So what is the Moss coefficient? So the Moss coefficient is KL. Okay. So this right here is the Moss coefficient that you would look up in a table for a particular type of geometry. Okay. So there's a table in the textbook that shows this, but for our purposes, if I'm going to ask you a problem with a minor loss, I'm not going to expect you guys to write down or copy the table into your cheat sheets or into your notes. I'll give you the Moss coefficient. Okay. All you guys need to do is you just need to know how to actually use it. Okay. So based on that Moss coefficient that's given, we can use that to compute the minor losses. So the head loss for the minor losses is equal to your loss coefficient KL multiplied by v squared divided by 2g. Okay, where v is, of course, the velocity of the fluid going through the pipe, and g is gravity. And so you're gonna do this. You're gonna compute this for every single minor loss that you have in the system, and a lot of times you're gonna have multiple of these. Okay. Okay, so you're going to compute this for every minor loss in your system, and then at the end, or I guess when you plug it back into modified Bernoulli, you're going to add all these together. Okay. All right. So once you have the loss coefficients, it's actually a very systematic procedure. It's a lot nicer than the major losses, because for the major losses you have to kind of really cross-reference with the Moody chart, which can get a little bit messy, especially for certain types of problems. You'll see in the last example we do today, it does get a bit messy. But for the minor losses, just know that for every minor loss, you're just going to add more losses to it. Okay. All right, so before we get into the example, I do want to talk about just a few specific minor losses and kind of explain a little bit in terms of why they occur and what their loss coefficients, specifically is. Okay. All right, any questions on this? Okay, all right, so let's talk about some examples of some minor losses and their coefficients. Okay, so the first one that we will go over is one that we will use in our example, a lot, which is a 90-degree turn. So let's say that you're designing a pipe, you're making a pipe, and you have to make it turn to go in a different direction. Okay. So a 90-degree turn is exactly kind of what it looks like. And so, okay. And so it's something like this. And so you have flow that's coming in, right? And then this flow then has to change direction. So in this case, it's making a left turn. And it continues upwards just like that. Okay. Okay, so just by going to return, you're actually going to incur a fair amount of minor losses. The reason for that is that the flow does not actually just kind of make a smooth turn. The fluids don't actually have like a steering wheel attached to it, right? And so what tends to happen is that the fluid is going to keep going in its original direction. It's going to crash into the wall, right? That is where the turn occurs. And then from after the crash, it's then forced to kind of change direction and go upward just like that. All right, so as you can imagine, crashing is usually not an energy efficient way to travel. And so by crashing, you are going to incur some losses. There's some heat that gets dissipated because of the viscous friction of that crash. Okay. What can happen sometimes as well is that you can actually have some recirculation zones as well. And so as the flow starts to change direction, okay, like I mentioned, most of the flow is going to want to try to continue along its original path. And so what can happen on the inner, elbow of the turn right there, you could have some flow that actually starts to swirl. Right, so you get a little bit of a tiny vortex that kind of occurs on kind of the inner, the inner part of the turn. Right, so we call a region like this a recirculation zone. Okay, and we'll see recirculation a bit, but as well in the other examples. But whenever you have recirculation, that's also an area where energy can get dissipated because the flow's not really going anywhere; it's just kind of going in circles. And because of that, viscous dissipation kind of adds on to that, which also further saps some. Okay. Now, for a 90-degree turn, the loss coefficient is actually very straightforward. Okay. And note the units for the loss coefficient. It is a coefficient, so it is unitless, right? But the loss coefficient for a 90-degree turn is 1.5. Okay. So in order to get the head loss for a 90-degree turn, you take the loss coefficient 1.5, you multiply that by the velocity of the flow going through the 90-degree turn, v squared, and you divide by 2g, and then that gets you your head loss for that turn. Okay? And if you have multiple 90-degree turns that you're going to see in a second, then you're just going to keep adding to that based on these terms. All right, any questions on that? Okay. All right, the next one that I want to talk about is a sudden contraction. Okay, so a sudden contraction is when, the cross-sectional area suddenly gets, very, very small in the flow direction. All right, so you have your flow like this. Right, so your flow is coming in from the left, and then flow is then forced to go into a very narrow passage. Okay, so ideally the flow should kind of follow this path just like this. Okay, and some fluid does do that, but you're also going to have some fluid, just like the 90-degree turn. It's just going to keep going. It's just going to crash against this wall just like that. Right, so that's going to cause some losses as well. Okay. And because of the sudden contraction, you're also going to have a little bit of recirculation as well. So you have some crashes in those regions, but also some recirculation here as well. All right. So a sudden contraction is another type of geometry change which causes a minor loss, right? So the contraction, and you're going to see for the expansion as well, is actually interesting. So the amount of minor losses actually depends on the ratio of the inlet area and the outlet area. Okay? So if we call the inlet area A1 and we call the outlet area A2, right? So A1 is the bigger area, A2 is the smaller one. right? The exact loss coefficient depends on the ratio of A2 over A1. Okay, so there's a graph for this. Okay, so on the horizontal axis for the graph, we have A2 over A1. The graph starts at 0.0 and it maxes out at 1.0. Okay. We can see that, an A2 over A1 of 1.0 basically means that the two areas are the same, right? So if A2 and A1 are the same, the ratio must equal 1. So on the far right of the graph, we have, basically no contraction at all. And on the left side of the graph, we have basically a very, very small contraction. Okay. All right, so this graph, quite interesting. So it actually starts at 0.5. Okay. So the biggest amount of minor loss that you can obtain for a sudden contraction has a loss coefficient of 0.5. And then it kind of follows this, mostly straight curve, but there is a little bit of curvature. So it actually starts out a little bit flat, and then it kind of accelerates. And then by the time it hits 1, you get a loss coefficient of 0. Okay. So you can compute your loss coefficient by looking at this graph. But most of the times, when you have a sudden contraction in a system like this, you're going to do so for very extreme ratios, right? So A2 is usually much, much smaller than A1. Right? And so in those situations where you're going from a very large area to a very, very small area, essentially we can assume that their ratio is going to be 0. And so in that case, it's pretty easy to read off the loss coefficient for this graph. The loss coefficient is going to be 0.5. All right, and so for most cases, where I'm going to ask you to compute something with a sudden contraction, it's going to be a big drop like that. So you can assume that 0.5. But just know that if you have a fairly modest kind of change in area, then the loss coefficient is going to be less in that case. All right, and then the final minor loss that we'll go over together, but just remember that there are a lot more of these, is a sudden expansion. Right, so a sudden expansion is going to be the opposite. Right? And so the opposite of a contraction is an expansion. So we go from a small area over to a large one, where we can once again quantify the inlet area as A1, the outlet area as A2. Right, and then we're similarly going to have another relationship between the ratio of these two areas and the corresponding loss coefficient. I always have this weird habit. Whenever I write, and it happens when I write and when I type these two. Whenever I type or write ratio, I just naturally want to add an N to the end to spell ration. I have no idea why, but it's just shortcutted my brain for whatever reason. So most of the times I catch it, but sometimes I don't. So if I ever write ration, I mean ratio. Okay, so the graph for that looks like the following. Right, so similar to the sudden contraction on the horizontal axis, we have a ratio, but it's not going to be the ratio of A2 over A1. This is going to be the ratio of A1 divided by A2. So just be careful of that. Okay. So these two are different, mostly just so that the graph itself can look the same, but it does make things a bit confusing. Okay. Vertical axis, we have KL. Just like before, our horizontal axis will go between 0 and 1. Okay. And the graph looks very similar, right? And so just like in the sudden contraction, if you have a ratio of 1, meaning your two areas are the same, then you're not going to incur any minor losses. And so your loss coefficient will be 0. Okay. Now, what's interesting here is that a sudden expansion actually incurs more losses than the sudden contraction. Right? So the loss coefficient for a ratio of 0.0 is actually 1. Whereas for the sudden contraction, it was 0.5. Right? So you do get a bit more minor losses for a sudden expansion like these. Okay, good. So these are just a couple of examples, but just note that, for every other type of, either geometry change or change in direction in a pipe, those loss coefficients are tabulated. So in my notes here, I actually have a reference to the table in the textbook that actually has these loss coefficients. I haven't obtained a new version of this textbook in over 10 years, and so I'm hoping it's the same number. But if you did end up picking up the textbook, this is table 8.2. All right, any questions on these minor losses here? Okay. All right, so then let's go ahead and move on to just examples from here on out. Okay. So let's talk about just pipe flow problems in general. So when you get a pipe flow problem, either on a homework or on the exam, there'll be something like this. Okay, so these problems here I would consider as practical problems in pipe. Okay. Now, we're basically going to combine everything that we've learned up until this point. So, computation of the Reynolds number to determine whether we're laminar or turbulent, computation of the major losses, computation of the minor losses. Now, what's interesting about pipe flow problems is that they come in different flavors depending on what you are trying to look for. So in that sense, it's pretty nice because you can look at a pipe flow problem and you can say, right away, this is a type 1 type problem. This is a type 2 problem. This is a type 3 problem. Okay. So most other subjects don't have this. And so, because depending on the type of problem that you have, it's going to tell you what type of methods and what type of approach you want to use. Okay. All right. So first one is type 1. So this is the simplest. Right? So in a type 1 problem, you are given the volumetric flow rate through the pipe. Okay. You might also be given the velocity. That's also fine too, but most commonly you're given the flow rate. Okay. Most of the times in practice, you're designing pipe systems. Most systems are rated by volumetric flow rate. Velocity is actually quite rare. Okay. So you're given in these types of problems, you're given flow rate and you're given the pipe geometry. Okay. And what you're looking for in a type 1 problem is usually going to be pressure drop, but then along the way to pressure drop, you're also going to compute the head losses as well. So we did a couple type 1 problems yesterday already. So we did one for laminar flow, we did one for turbulent flow. Now, granted, the turbulent flow example we did only had major losses, but type 1 problems are fairly straightforward. Okay, so it's just basically just an application of Bernoulli's after you compute all the losses, and then from there you can compute pressure differences from. Okay, all right, type 2. All right, and what you'll see is that the different types of pipe flow problems, you're given different things and you're expected to find other stuff. Right, so in type 2 problems, you are given the pressure difference. Right, and sometimes you're also given the head losses as well. Okay. So in these cases, you're given the pressure differences, you're given the pipe geometry, and what you're looking for is to determine the flow rate. So it seems fairly straightforward, right? And so, it's kind of just a riff on type 1, where you're given different things and you're expected to compute something else, okay? So type 2 problems are very common in practice because a lot of times when you're designing a piping system, a pressure difference is usually a constraint of some kind. So, let's say you're designing the piping or the plumbing in someone's house, right? Usually, when you draw water from the water main, then, you know exactly what pressure it's at. And so you have to kind of design around that. And then you have to determine what the flow rate is based on other information you have, right? But type 2 problems are actually more complicated than type 1, right? Because you're not given the flow rate, you actually are not able to compute the Reynolds number. Right? And that's actually a big deal because Reynolds number, first of all, Reynolds number tells you whether your flow is laminar or turbulent. And so, just from the start, you have to make a guess whether your flow is going to be laminar or turbulent. But, when you compute major losses, you also need to use the Moody chart. And if you remember from yesterday, the Moody chart, where you are in the Moody chart depends on your Reynolds number as well. So you have to kind of make a guess on that as well. Okay. So type 2 and type 3 problems are actually quite complicated because you have to actually do a little bit of guess and check, which, what we call in engineering iteration. Which, iteration is not the most difficult thing, but it can be frustrating because it kind of feels like you're doing the same problem multiple times, just with slightly different numbers. But, just know that for type 2 problems, because of that complication with the Reynolds number, you may have to do it multiple times with slightly different guesses. Okay. Okay, and then type 3, you can probably kind of guess what type 3 is all about. So in type 3, you're given the pressure difference and you're given the flow rate. And you're going to be asked to compute some aspect of the pipe's geometry. 9 times out of 10, it's going to be the pipe diameter. And so for type 3 problems as well, right? So if you remember how the Reynolds number is computed, right? Reynolds number also depends on the diameter. You know, the velocity also depends on the diameter as well. So if you're given flow rate, you actually can't even convert that to velocity because you don't even know what the diameter is, or that's what you're solving for. So for type 3 problems, you have the exact same problem as type 2. So, you have to kind of start with a guess for things and then kind of give that a try, check your answer, and then you probably have to do it multiple times in order to get the right solution. Okay. If you're good, if you're lucky and you guess well, then you could get it in one shot or two shots. That's not uncommon. If you're doing the homework, then you kind of know what the solution is, and so you can probably guess it in one shot. But in practice, you may have to try multiple times. And so the second example that we do today, we'll show you how to. Okay, and so from here we just have examples. And so I have one type 1 problem, and I believe my second example is a type 2 problem, or type 3 problem. Okay. All right, any questions before we jump into it? Okay, all right, so let's go ahead and jump into these examples. Okay, so first example is going to be a type 1, but we are going to have a fairly complicated geometry. All right, so let's assume that we have water flowing through a pipe. Right, so our water here has a density, we're going to assume is 1,000 kilograms per meter cubed, and has a viscosity of 8.9 times 10 to the minus 4. Right, so we have water flowing through, and it's flowing through a copper pipe with a diameter of 2 centimeters. So that's good. We're given the geometry of the problem, so that helps us. Okay. Okay, and then we're also given the flow rate. So we're given that the flow rate is 750 milliliters per second. So we're given the flow rate as well, which is good, right? So we can see from the problem here, we are given the geometry. We're also given the flow rate, right? And so we can kind of guess what the problem is going to ask us to do, because this is a type 1 type problem. All right, and so based on that, we know the problem's probably going to ask us to compute pressure drop or to compute head losses along the way. Okay, and then now let me go ahead and draw our geometry here. Okay, so we have water that's coming in. I guess we'll call this location 1. All right, so we have water coming in. It's going to make a 90-degree turn to the left. Going to go up. Okay. That was a little bit better. All right, it's going to go up for a little bit, and then it's going to make another 90-degree turn to the right. Okay. And then just because it's going to make another 90-degree turn to the left. And just because maybe we just had a bunch of these 90-degree fittings, make another 90-degree turn to the right. All right, so we're going to break up this pipe here. Right, so we're going to isolate all the 90-degree turns. So I'm just going to highlight them just to kind of make them a little bit clearer. All right, so everything I've highlighted there is a 90-degree turn. And oftentimes you'll see this too, just because to make a 90-degree turn, you need some kind of fitting to kind of make that happen. Okay. I'm going to label each segment of pipe with a letter, right? Just so that, we know what, to compute for those ones. Okay. So for this first section, we'll call it section A. The first 90-degree turn we'll call section B. We have a straight section in between our two 90-degree turns. We'll call that section C. Next one, call section D, E, F, G, H, and then I. Right, and so for each section, we're going to compute the head losses. They're either going to be a major loss because it's a straight section, or a minor loss because they are a 90-degree turn. Okay, and then let's put some lengths here as well. So the length from the starting point up into the first turn, we're going to say this is 4 meters. Okay. The length between the two 90-degree turns B and D, we're going to say this is 3 meters. Right. Of course, this is not drawn to scale. The distance between D and F, we're going to say is 2 meters. And then the vertical distance between F and H, we'll say this is 1 meter. And section I, we'll say this is 10 meters. Okay. And so given all this information, what we want to do is compute. Okay. Just like a very classic type 1 problem, we're going to compute the pressure difference between the inlet and the outlet. Okay, so this is a very standard pipe flow type problem. It's a type 1, so it's the easiest. And so all we're going to do is just apply a modified Bernoulli. We are going to have a height difference, and so I think this might be the first time in the class we did an example with where our height's going to change. But we also need to compute the losses as well. So we have major losses in the straight segments A, C, E, G, and I, and then minor losses for the turns, section B, D, F, and H. Okay, any questions on just the setup for the problem? Okay, all right, so let's go ahead and get started. All right, so let's go ahead and write out our modified Bernoulli. Okay, so we'll say this is let's see. We'll go 2 to 1 in this case. We'll go P2 divided by rho times G plus V2 squared divided by 2G plus Z2 is equal to V1 divided by rho times G plus V1 squared divided by 2G plus Z1 plus HS minus HL. Okay. All right, so that's just our Bernoulli, modified Bernoulli equation. So Bernoulli with the shaft head as well as the head losses. All right, so let's go ahead and simplify this. Okay. First thing we're going to note is that there's no pump and no turbine, and so there's going to be no shaft work here. So this is just flow in a pipe. Let's see. Right, so we can just go ahead and cancel that term out just like that, right? Also, our pipe is constant diameter, and we know that our flow is steady. And so just by conservation of mass, we know that the velocity at the inlet and the velocity at the outlet have to be the same. All right, and so if we kind of rearrange the terms a little bit, and so essentially we want to solve for P1 minus P2. Okay. Right, and so we rearrange the terms a bit. Right, so I'm going to skip the algebra just because I want to make sure I get through the second example too. Right, so we have P1 minus P2. We're just going to rearrange algebraically is equal to rho times G multiplied by Z2 minus Z1 plus the head losses multiplied by rho times G. All right. So we can compute Z2 minus Z1, that's pretty easy, right? And so if we look at the height difference between the outlet and the inlet, right? And so each time we go up, we're gonna add that distance. And so we first in section C, we travel upward by an amount of 3 meters. And then in section G, we travel upwards by an amount of 1. Okay. So the total height difference between the outlet and the inlet is 4 meters. So the Z2 minus Z1 in this case is 4. All right. So pretty straightforward. We know the density that was given to us in the problem. We know gravity. Unless otherwise specified, we can assume that we're on planet Earth, right? So we're not on the moon or any other planet with any other weird gravity. Okay. And so the last thing we need to compute before we can compute the pressure differences are the head losses. And we need to have both the major losses from the straight sections and the minor losses from all the 90-degree turns. Now it may seem tedious because it may seem like we have to do this however for each section individually, but we are going to be a little bit smart with how we do our work because we know that all the minor losses they're all occurring due to 90-degree turns, right? And so we can kind of lump all those together and just add all of those loss coefficients, okay? And for the straight segments, even though they're different, they're kind of separated, they all kind of add additively as well, right? So let's start with the major losses. All right, so if you go back into our notes yesterday, we know that our formula for the major losses is equal to the friction factor multiplied by the length of tubing divided by the diameter multiplied by the velocity squared divided by 2g. Okay. All right. So once again, we have a lot of this information. So we are given the diameter of the problem. We know gravity. We haven't computed velocity yet, and I apologize. We probably should have done that first because we need the Reynolds number. But we can compute it because we have the flow rate and we have the cross-sectional area. Okay. Now friction factor. We are going to need to compute this from the Moody chart. Okay. And so to do that, we are going to need the Reynolds number for that as well, right? But here's where we're going to be a little bit clever. So this length right here, right? Normally, you could probably you can compute the major losses for each segment individually, or what you can do is you can interpret this as saying this is the total length of straight tubing in our entire system. So we can just make one computation for all the major losses by just adding up all the straight segment lengths. Okay, and so if we do that, right, so we have the length of segment A, which is 4 meters, the length of segment C, which is 3, then 2, then 1, then 10. Okay, so let's go ahead and add those up. So L total is equal to 4 plus 3 plus 2 plus 1 plus 10. Okay, where this 4 was the length of segment A, this 3 was the length of segment C, the 2, on my alphabet, 2 was the length of segment E, 1 was the length of segment G, and the 10 was the length of segment I. Okay. So we add all those together, and what we get is 720. Right, so let's plug that in there, and then what we can do from that is that, we're going to compute the major losses of the entire system, so we don't have to do each segment individually. You can certainly do each segment individually. You're going to get the same answer once you add them up, but this just kind of saves you a little bit of time just because we know all the straight segments are this. Okay. Okay, good. All right, so then let's get started on computing the friction factor. Okay. So first thing we need to compute friction factor is that we do need to compute the Reynolds number. Right, so our Reynolds number is rho times the velocity times the diameter divided by the viscosity. Right, so we're given most of that in this problem. So the density, the diameter, and the viscosity are all given to us. The only one that's not given to us is the velocity, but we can obtain it. Right, the number of velocity is nothing more than just the flow rate divided by the cross-sectional area, where cross-sectional area in this case is I/4 d squared. Okay. All right, and so if we do that for this problem, right, we plug in our flow rate. So our flow rate given to us was 750 mils per second, which is, remember, a milliliter is a centimeter cubed, and the diameter is 2 centimeters. Okay. And so we do that, we get a velocity of 2.39 meters per second. We plug that in to our Reynolds number, right, along with our density, along with our diameter and our viscosity. And what we get is a Reynolds number of 53,647.7. Okay. Which, if you want to approximate it, just for the sake of the Moody chart, this is 5.4 times 10 to the fourth. Which, as you can see, so if you remember from yesterday, our threshold for turbulent flow is our Reynolds number being greater than 4,000. This is definitely greater than 4,000. So we indeed have turbulent flow. Okay, so that means our friction factor has to be read off the Moody chart. Okay. Okay. All right, and so remember, to use the Moody chart, we need the Reynolds number, which is what we just got here. But we also need to know the ratio of the surface roughness divided by the diameter. Because remember, this quantity is going to tell us which curve in the Moody chart that we need to follow. Okay. Okay, so for our problem, we are given that our pipe is made of copper. For copper tubing has a surface roughness of about 0.0015 millimeter. Which, is something you can look up in a table. That's kind of the annoying thing with pipe flow is that, a lot of the information you need to do the problems are in tables and they're not all in the same table. You have to look at different tables and different charts. Okay. Right, but for our purposes, this is something I would probably give to you in the problem. I wouldn't expect you to look this up, yourself. Okay. And so if we compute this diameter, epsilon over d, knowing that our diameter here is 2 centimeters. then we obtain a ratio of about 7.5 times 10 to the minus 4. Okay. Which, if you want to round this up to a particular level that's in our Moody chart, this is the same as 0.000. Okay. So based on that number there, and based on the Reynolds number that we just computed, if we use those two informations on the Moody chart, okay, that gives us a friction factor of 0.02. Okay. Right. So now that we have a friction factor, we have everything that we need to compute the major losses. And so we're just going to plug everything into this formula here, right? Again, using our total length of all the straight segments. Right? And so then what we get for our major losses for this problem is 5.83 meters. Okay. Good. All right, so those major losses we can plug into our modified Bernoulli, but we also need the minor losses from all of the pipe vents. Okay. But are there any questions on how we obtain the major losses? Okay. All right, so let's go ahead and compute the minor losses. So thankfully, the minor losses are fairly straightforward, right? Because they're all the same. Right, so for the minor losses, we have basically 4 90-degree turns. Okay. And if you think back to, when we discussed minor losses, each 90-degree turn has a loss coefficient of 1.5. All right, and so if we basically plug those in, right, and so we're going to have the loss coefficients for all 4 of the 90-degree turns. So that's segment B, segment D, segment F, segment H. Right? This is KB plus KD plus KF plus KH. Well, all of these are 1.5. Right, and then we're going to multiply that by V squared over 2G. Where we have the velocity from the previous part. This gives us a minor loss of 1.75 meters. All right, good. All right, so now that we have the major losses, we have the minor losses, we can compute the total head losses. Okay, so total head loss is just going to be the sum of the major losses and the minor losses. Right, which is 7.58 meters. Okay. All right, and then now that we have the head losses, we can then go all the way back up to our modified Bernoulli. Okay. And we have everything we need here to compute the pressure difference. Okay. So we plug back into modified Bernoulli, we get P1 minus P2 is equal to 113.5 kilopascal. All right, so that's a type 1 problem. So type 1 problem is, believe it or not, very straightforward. I know there's a lot of steps involved, especially with computing the head losses, but it is still very systematic. Any questions on type 1 problems? Okay, all right, so I'm trying to rush here, so I want to get through the second example. I may not get through all of it, but I may post, just because I know the homework is due this weekend, I may post a supplement from my office just to kind of finish up this example if we need to, okay? Okay, so the second example here is a type 3 problem. Okay, so in this problem, we are given a similar pipe. This one doesn't have any bends, and so we don't have to worry about minor losses, but we are going to solve for the pipe diameter. Okay. Okay, so for this problem, we have our fluid is now air. Okay. So the density of air is 0.00238 slugs per feet cubed. Okay. And our viscosity was 3.74 times 10 to the minus 7 pound second per feet square. All right, so we have air that's flowing through an iron pipe. Okay, where we're given in the problem that the surface roughness for iron is 0.0005 feet. Okay. So this would be pretty typical in terms of a problem that I would give you. So I would just give you the surface roughness in the problem. This is not something that I would expect you to look up. Okay. Right, and we're also given the flow rate. And so we're given that the flow rate is 2.0 cubic feet per second. All right, so we're given flow rate in this problem, so we know it's not a type 2. Okay, because for type 2 problems, you would have to solve for the flow. Okay, and so what we're also given is that for a 100 feet segment of pipe, a straight segment, so that tells us our length, and so our length for this pipe is going to be 100 meters, or 100 feet, excuse me. Okay. So for a 100-foot section of pipe, what we're given is that the engineering constraints of our system state that the pressure drop should not be more than 0.5 pound per square inch. Okay. So I know the wording is a little bit different in this one, but this is a very typical type of wording of a problem that you would get in a typical engineering system. Okay, so we're given the length here, and we're told that the pressure drop should not exceed 0.5 psi, basically, okay, pounds per square inch. And so what we're going to do is we're going to assume that the pressure drop is 0.5 pound per square inch, and then solve for basically the smallest diameter that we can have in order to obtain this pressure drop. Okay, and so what we want to do is compute the pipe diameter. Okay. So don't be thrown off by the wording. And so a lot of times you'll see wording of they'll say the pressure drop has to be at least this much or it cannot exceed this much. For your purposes, when you're solving those types of problems, you're gonna set that equal to that, even though the problem may say exceed or less than, right? So for this problem, we're gonna set the pressure drop equal to 0.5 psi. Okay. Okay, and then we also see from the problem, because we're solving for an aspect of the pipe geometry, this is a type 3 problem. Okay. All right, so what you're going to see is that, missing the pipe diameter is actually going to be a pretty big deal because that's going to prevent us from computing a lot of things. Okay, but just like our previous example, we are going to start with the modified Bernoulli. All right, so we have P2 divided by rho times G plus B2 squared divided by 2G plus Z2 is equal to P1 divided by rho times G plus V1 squared divided by 2G plus Z1, okay, plus the shaft head minus the head losses. All right. Modified Bernoulli is where we need to start because this has everything that we need. Okay. All right. So I know we're not given a figure in the problem, but the problem did not suggest any kind of height differences. And so we can assume that the two heights are the same. So Z2, Z1 are the same. We're also not told in the problem that there's any kind of pump that's driving the flow. There's no kind of turbine that's extracting energy. So the shaft head also is 0. Okay. And then just like the previous problem, we know the pipe has a constant diameter, right? So there's no expansions and there's no contractions. And so by conservation of mass, the velocities also have to be the same as well. Okay. And so if we rearrange this formula a little bit, and so you can see a lot of it's going to cancel out, we get P1 minus P2 is equal to head losses multiplied by rho times G. Okay. So this seems like, we're very close because this formula we got here is straightforward. And in fact, the problem already gives us the pressure drop. Okay. So it looks like we're sitting pretty, right? Because we know the density that was given to us in the problem as well as the gravity. Right? And so all we have to do is plug in an expression for the head losses. But unfortunately, this is where things kind of get complicated. Okay. Now we are in a good position here in the fact that we don't have any minor losses. And so all the head losses here are just going to be major losses. Okay. Okay, so let's go ahead and plug in our formula for that then. Okay. All right, so we have delta P. All right, I'm just going to substitute delta P in for P1 minus P2 because that's given to us is equal to rho times G multiplied by our formula for the major losses. And so remember, our major losses are F, friction factor, multiplied by the total length, divided by the diameter, multiplied by the velocity, divided by 2. Or we can simplify this a little bit because we have a gravity in the numerator and a gravity in the denominator. We can go ahead and cancel both of those out. And so after that, what we're left with is delta P is equal to rho times the friction factor times the length divided by the diameter times V squared divided by 2. Okay, good. So what we want to solve for is D, right? So the diameter is an unknown in this problem. The problem is, we also don't know the friction factor, and we're not given the velocity either, okay? So let's start with velocity because that one is a bit easier. And I realize I'm just about out of time. So if you guys have to go, please don't feel like you're trapped here. Remember, all this is recorded, so I'm gonna post this. But I think I just need maybe 5 more minutes, and so I'm just gonna keep going. But just to kind of finish this, just so you have for your homework. But yeah, if you need to leave, just don't let me keep you. Okay. All right. So let's go ahead and plug in for the velocity first. Okay. So we are given our flow rate in the problem. So just like we did previously, our velocity is just going to be Q divided by the area, where the area in this case is going to be pi over 4 times d squared. So we can actually plug in for all of these quantities here because we're given Q in the problem, right? We know the flow rate, we know pi, and we know 4, right? The only thing we don't know is D. So we're going to leave that as an unknown, okay? And so what we obtain from this after plugging in, what we get is 2.55 divided by D squared. Okay, so let's go ahead and plug this back in for the velocity here. And remember, we have velocity squared, so we have that entire thing squared, right? All right, so you have delta P now is equal to density times friction factor times length divided by D. I'm going to pull out the 1/2 just to make things a bit easier. And then we have 2.55 divided by D squared quantity squared. All right, so we have a little bit of more arithmetic here. So we are going to keep plugging things in, right? Keep in mind, we cannot plug in for F just yet, but we can plug in for the density, we can plug in for the length, we can plug in for the pressure drop, okay? All right, quick note on the pressure drop, we do have to convert the units here because what's given to us in the problem is that this is 0.5 pound per inch squared, okay? But all the other length units in our problem are actually given in feet. So let's actually convert this to pound per feet squared. Okay. Okay. And so 0.5 pound per inch squared is 72 pound per inch. Okay. Okay, so let's go ahead and plug that in, right? And so we have 72 is equal to, let's see, we do all the arithmetic here, we get 0.7738 times the friction factor divided by d to the 5th power, okay? Because we have 1 power of d that comes from the L over d term and a d to the 4th term that comes from the d squared term, okay? All right, and so if we solve for d here, we get d is equal to 0.404 times f to the 1/5. Okay, And now we're stuck because we don't know what the friction factor is. And we can't even plug into the Moody chart, right? And so because for a Moody chart, we need a couple things. So we need both the Reynolds number and we need to know the ratio of epsilon over d. Okay. So both the Reynolds number and our ratio epsilon over d depend on the diameter. And so because we don't know what the diameter is for solving for it, we can't compute the Moody chart, and so we would be stuck here. Okay. So this is when you need to kind of guess and check a little bit. Okay. Okay. All right. And so the way this is going to work, we're going to guess a value for f. Okay. Right. And so you can look at even though we don't know exactly where we are on the Moody chart, you can look at kind of the rough magnitudes of f from the Moody chart, get something that's somewhat reasonable. Okay. Once we guess f, we can then plug it in and solve for d. Okay. Right. We just use the formula that's box there to solve for d. Okay. Then once we have the diameter, we can then use that to compute the Reynolds number and epsilon over d. Right? Because that diameter was the missing piece. And then based on that, we can then check our results. Okay? And so ideally, if you made a good guess for the friction factor and you end up computing the Reynolds number and epsilon over d, when you check it in part 4 or step 4, it should match what you guessed in part 1 or be relatively close. Okay. It doesn't have to match exactly, right? And so, don't try to match it up to the 7th decimal place. That's just crazy. But it should be relatively close enough. Okay. Okay, so that's the procedure. And so, the details for that are in the notes. I don't want to keep you guys any further until 6 o'clock, but that's how you would solve this problem. So, if you're good at guessing, you would basically solve this in one shot. If you're not good at guessing, then you have to repeat this 3 or 4 different times until you get kind of the right friction factor. Okay. All right. Any questions on this before we wrap it up for today? Okay, all right. So that's all we have for time for today. So thank you guys for coming and thank you guys for staying a bit late. If you do have questions on these type 2, type 3 problems, definitely send me an email. If there's enough people asking me questions, then I may post an additional video to kind of get more details on this. But just note that it is in the lectures. Okay. So thank you guys for coming today. Hope you guys have a good weekend, and I will see you guys next week.